Hey guys, my name is Zach Lasser, and I'll be talking about Lab 5, which I did over projectile motion. In this lab, I observed a basketball being shot from the free throw line. In order to observe projectile motion, I compared the motion of the basketball to Newton's second law using V idle. The results of this lab were that the computational model fit closely to the observed results, but there was also some discrepancies between the graphs, and these were due to the fact that I did not account for drag force and other external forces that were acting on the ball, such as the wind. Projectile motion, this is a summary. The x component of velocity, the velocity in the x component is equal to v equals delta x divided by delta t. And for projectile motion problems, the velocity in the x is constant over time. So it's a different equation than the y component. The y component of velocity is equal to Newton's second law equation, which is v final equals v initial plus f net divided by mass times delta t. If we head over to tracker, we can see that I set my calibration stick to equal 10 feet, which is the standard height of a basketball goal. My brother is standing here, and I'm about to shoot the ball, and I set the axis to the center of the ball, so the initial position is close to 0, 0, 0. When you run it, you can see it's making a parabolic curve. So in the y direction, it is a parabolic curve, but in the x, this is a position versus time graph. It's a straight line, meaning that the velocity is constant, which was what we stated earlier. I then copied all the times and y positions over to an Excel file to compare to the computational model. Here's my code I used for this lab. The mass of the ball is equal to 0.624 grams, or 0.624 kilograms, my bad. And then the initial position of the ball is equal to negative 0.028, 0.028, and 0 meters. And the initial velocity was 0 since it was starting from rest. We had a set like g equal to 9.8 meters per second squared in order to calculate the force of gravity acting on the ball. And here we set, this is where we do the Newton's second law equation of velocity equals velocity plus f net divided by mass of the ball times delta t. And this is going to output all the y positions over time over 0.902 seconds using a time step of 0.01. And after you run it, I copied it all over to an Excel file. And once I compared the Excel file graphs with each other, and the computational model is the gold line, and the observed is the yellow line, and the yellow line is the one that's basically the lower one, and the gold one is the computational model. And the reason that it overshot the observed results is mainly due to the fact that I did not account for the external forces such as wind and drag force, and not accounting for drag force is pretty big, just because the basketball actually had a decent mass, so that drag force was actually like you can tell the difference. You can see the difference. And then in conclusion, I observed the projectile motion of a basketball and compared it to a computational model that was using Newton's second law. I should have used drag force in my code and accounted for the other external forces. And what I learned from this lab is I learned that the velocity in the x direction for a projectile motion is constant and can be calculated in a different manner than the y component velocity. That's all I have, so thank you guys for watching.